So now that we're confident in calculating moments, we're going to extend on the idea of equilibrium from last year. Equilibrium was when a particle or an object was at rest, and we realized that the forces would balance. The forces to the left would equal the forces to the right. The forces up would equal the forces down. And because of that, the object wasn't moving. It was at rest. It was at equilibrium. Well, we're going to do a similar thing with moments. Now, we should be able to calculate moments, and if a body is at rest or is in equilibrium, well, clockwise moments should equal anti-clockwise moments, as well as upwards forces equaling downwards forces, and forces to the left equaling forces to the right. So really, that concept is what we're going to be looking at in all of our problems to do with equilibrium. Okay, so for each and every question, the strength is going to be in the diagram that we use to model the situation. I will always just reproduce my own diagram because I'm likely to add things to it that aren't in the original diagram if given in the question. Okay, so let's get those supports, A and C. The rod is called AB, and we'll give it some lengths. What we've got to be careful of is reaction forces. Wherever the rod comes into contact with supports, there is actually a reaction force. Let me just label these underneath and add in those two reaction forces. I try to give them a subscript since we don't know that they're the same, so to call them both R will not be correct. So RA and RC, or R1 and R2, whichever you prefer. Now we can read through the question for some extra information, and almost straight away we were told we're working with a uniform rod. This means the center of mass for this rod, we're going to model it right at the center of the rod. Since it was a 3-meter rod, we should be modeling it 1.5 meters in. So actually, I'm going to redraw some of these distances. So here's the weight of the rod. And rather than the 2 meters, I'm more interested in the 1.5 meters and the 0.5 meters. So I recommend you're always showing distances in between consecutive points of interest on the rod. Okay, next we'll get into our strategy. The first thing to do is to resolve forces vertically. Everything up equals everything down. R1 plus R2 equals 20 newtons. We can come back to this later. Next, we need to choose a point to take moments from. I recommend that you always choose one of the support points to take moments from. Some people choose the end of the rod or the center of mass. Much better that you pick one of the support points. Main reason being, it eliminates one of the reaction forces, and we don't need to consider it in our calculations. So let's go ahead and take moments from A. Okay, so the distance to the weight is 1.5 multiplied by 20. That's the moment. That's the only clockwise moment. And my anti-clockwise moment is the 2 meters to reaction 2 multiplied by R2. All right, some sensible rearranging, and I can get a value for R2. It's going to be 15 newtons. And if I know R2, going back to my original equation from resolving forces, I can quite quickly deduce that R1 must be 5 newtons. And there we go, we've found the magnitude of those two reaction forces. Resolving vertically and taking moments is always the strategy. Well, let's go again with another question. This time there are additional forces. We've got a person who's standing on the beam. We're told once again that the beam is uniform, and we know the mass of the beam, and we know its length, and I know the distance from the end of the beam to each of these supports. So that's what I've got on the diagram so far. I'm going to add in the reaction forces. All right, always reaction forces at these support points. In the question, we were actually told the reaction at D is twice the size of the reaction at C. So I refer to C as R1 and the reaction force at D just 2R1, just to show the relationship and that it's double the size. If I didn't, I would have too many variables to work with later on in the question. Let's go ahead and model this person, this man who's standing on the plank. So we know that he has a weight of 80 g and he's standing at a point E, which we don't actually know. So I'm going to label the distance from the center to the man as X. The space we have over here will be 1.5 minus X. And I'm going to go ahead and use these variables, these lengths, and these forces to solve and work with the rest of the question. Without this model, this diagram to this much detail, it would be quite difficult to maintain accuracy through the rest of our working out. But let's get to it. We'll start by resolving vertically, as always. So we get 3R1 equals 120 newtons. So straight away, R1 must be 40 newtons. Next is taking moments and just choosing somewhere smart to center those moments. We can go ahead and take moments around C. Actually, let me just label all of the points on the diagram. That's it. And taking moments around C. Okay, so we've got two clockwise forces, being the 40 newtons, which is 1.5 meters away. And also the 80 newtons, the weight of the man, which in total is 1.5 plus the unknown X distance away. So those two moments are added and should equal the anti-clockwise moment, which altogether is going to be 3 meters multiplied by 2R1. All right, so really we're trying to solve, so let's just expand and simply arrange and get a solution for X. And that leads to an answer of X equals 3/4 or 3/4 of a meter. All right, be really careful. Let's look back to the model. That is only the distance between the center of mass and the position of the man. The question had asked for the distance AE, the distance from A to the center of the man. So all in all, that's going to be 2.5 plus our X value. So that's 2.5 plus 3/4, which gives us 3.25 meters. Reading the question well and producing a clear and strong diagram that was labeled fully allowed us to resolve vertically and take moments accurately, which led to an equation and basically some algebraic manipulation for us to solve that question fully. Also, be careful, this is applied. Just finding X isn't always going to be the answer we're looking for. Understanding the context that we needed the whole length from A to E, that's the answer that we're looking for. Be really careful to check you've actually answered the question at the end. And for our third example, we'll look at a situation where the beam or the rod is not horizontal. So we've been told that a uniform rod is hinged at the point P, held in equilibrium, there's an angle of 50 degrees and a force of F acting perpendicular to the rod. So I can just add some lengths to the diagram, and really here I'm just going to solve with moments. The only unknown involved is that force. So let's go ahead and take some moments as we're used to. So I want the perpendicular distance to the line of action for the force that is the weight. We've looked at that a few times now. that perpendicular distance is going to be the hypotenuse multiplied by cosine 50. So 1.5 multiplied by cosine 50 is going to be the distance, and then multiply that by the 8g to get the moment. Okay, so that's our clockwise moment, and that should equal the anti-clockwise, which is a bit easier to calculate. It's the length of the rod multiplied by the force. They're already perpendicular. So that's going to be 3 multiplied by F. Let's just rearrange, and that will help us to find F. And we end up with F equals 25.2 newtons. So this time round, just taking a moment was enough for us to solve. But as I said before, your strategy is resolve vertically, take moments, and you should have all the information you need in front of you.